Howdy, we are a segmentation fault team. We are focusing on hardware fuzz testing. Team members include Benjamin, Journey, Ethan, Ryan, and our advisor is Rahul. So basically, what is hardware fuzzing? Essentially, it kind of comes off of software fuzzing, where this technique was used to run inputs into some code, and the code would then mutate those test cases and run back through it. And essentially, it would try to cover the most amount of code in it and try to find bugs. And so hardware fuzzing is taking that, but just applying it to newly designed processors and chips. So that's kind of essentially what hardware fuzzing is and what we're working on. The idea of it is to try to cover as much of the processor as possible and as fast as possible. Because now with Moore's law coming out, for decades, transistors and processors have become more and more complex and larger throughout the years. And so it's important that features like this are becoming more relevant in the hardware design world. So this is a hot growing topic that's becoming more and more popular.
So the way that we were performing the hardware fuzzing for our particular project, we were using a piece of software called VHUZ, which is essentially a way to simulate a piece of hardware on a machine rather than using an actual chip. And so we were able to, with VHUZ, we were able to simulate 3 different processor architectures. They were named Rocket Core, CVA6, and Boom. And so the way that this software works is that it would take an instruction generator and turn it into a seed, which would then take those seeds and put them into the input database, which is where all of the different test cases would be stored that we would use to input to the processor. And then while as those input test cases were input to the processor, they were also being mutated so that we could generate new test cases, and those mutations were then pushed to the back of the input database, and whatever was in the front would be pushed into the processor as an input. So we would basically have a first in, first out kind of methodology to that database.
Right. And our project was entirely based on changing this from a first in, first out to something a little bit smarter. We ended up with a process called coverage-based test case selection. So instead of going from a first in or first out, we hypothesized that if there are test cases that already increased coverage by running them, and then we mutate those test cases may be more likely to increase the coverage as well. So what our code first does is that our code will rank what type of coverage of these 5 line, branch, conditional, FSM, and toggle coverage are most and least needed for the entire processor for that specific iteration of VHUZ. The mutated test cases will know what their parent or the test case that they were mutated from. They will know the coverage of their parent test case, and they will know which of those types of coverage was most improved from that case to where we are right now. And then our test case selector will select the test cases that had parents that increased coverage in those most needed types. And then those test cases will be the ones that are fuzzed. In the event that we don't have enough test cases that have a specific type, then our code actually ranks what is most needed, and then it'll move on to the next most needed all the way until the end. And if it reaches all the way to the end, then it'll just take the first 10 like otherwise.
So as for our results, what we saw when we ran the fuzzer with our new feature versus the first in, first out method, there really wasn't much improvement that we could see. The original coverage there is plotted in that first graph, and then we have the following graphs to show the direct comparisons of the original and the fuzzer with the new features. It's a little small, but if you look in really closely, you can see that on average, the first in, first out system actually performed either the same or a little bit better than our new feature. We can move to the next. So here is the coverage of boom, as well as a CVA6. CVA6 looked like it didn't perform quite as well, so there was a difference between the processors and how the feature affected it. In conclusion, what we did was we assigned the test cases importance, and that was according to their coverage increases. When we scheduled it to mutate the important test cases first, it looked like it performed pretty similarly to the first in, first out method that was used in the original fuzzer. And of course, since we saw that there really wasn't much improvement, it suggests that we could try to work on that further, maybe use a different feature for importance or assign it in a different way.
Right. And one upside of this is that now that we have built out the system, there is a system for selection that isn't first in, first out. So if there is ever a correlation between other types of coverage and test cases, then our code that exists can be used as a baseline to implement that feature in DHUS. So silver lining. Yeah, and I think that's all we have. Thanks for paying attention, and have a good one.